So every foot of this beam has 650 pounds on it. Okay? And the way that we can calculate this is we can say that the total load within this block color pencils are good for this, maybe. The total load is the area of that block that I just colored. It's got a height of 650, it's got a length of 20. And if I work out my units, I take height times length gives me the area, 650 pounds per foot, times 20 feet, cross off the feet will give me pounds, so I'm consistent with my other units of force.
So for our homework one, are we assuming that it doesn't have a uniform density?
Correct, correct. And if you want to practice with one and add it in, that might be a good thing to do too. In this case, we don't have to do that. We could just say RAY plus RBY minus 1100 equals 0. Right, for our homework problem, that's that. There's actually one that's, next one down on the list that includes a uniform load. And we can do that one on the board if you'd like a little practice and have one in your, another one in your arsenal that you want. Does this step make sense? Okay. So now we apply, yeah. Yes, oh, absolutely. Yeah, because it's so easy to drop one of these pieces if you don't do that. Yep. Yes. Yes, dimensional analysis. And I don't know, maybe the PowerPoint will do this next, but I'm doing that. Right? And now I've got everything in pounds. So now I apply algebra. And I add 4,000 pounds and 650 times 20 to both sides of the equation. And that's what they've done there. So I got FYA plus FYB equals, now here's where, Joel, the positives make sense, right, and negatives. And now I've got 4,000, and this times this equals 13,000. I can add those two together because they're the same units. And I get two unknowns equals 17,000. They are not each 17,000 divided by 2. We don't know that, we can't prove that. So it's just that we've got two unknowns going on, and we happen to know that they both equal 17,000, whatever they are. So this is the point where I say, hey, wouldn't it have been convenient if we would have done something else before this to solve one of those two on the front end? And we use the moment equation to do that. So what we're going to do, now that we've shown that this is maybe not the way to go as our first step, do the moments next, we'll solve one of those two, and then we'll come back and plug in the known value and solve the other one. Write down every step. This is something that is easily lost, and when you're doing it in January or February, like, what? I can't remember what we did.
Just so I'm clear.
Yeah.
4,000 pounds is some load on the beam.
Yep, that's that one right there.
13,000 pounds is the weight of the structural value.
No, it's a load applied on top of it. It's the 650 pounds per foot. So the original loading on the beam was a uniform load over the top of 650 pounds per foot. It's not necessarily the load of the structure. It could be the load of the structure plus a design load on top of that. That's the tributary width on top of that beam.
Would it include the weight of the beam?
Most likely, yes.
And then possibly something.
Yes, so when we had our previous PowerPoint, we had dead load of 40 pounds a square foot and live load of 100. And then we calculated that times the 6'8", remember that calculation? That's what that kind of represents with a different, it's got a different number than that, but that's what that uniform load is.
So it's dead and live.
Yeah, it's dead and live in this case.
Beam's part of the dead.
Beam's part of the dead. All right, so next step, and they might actually, yeah, they kind of did this little animation for us to show what they call an equivalent concentrated load, and I think that they're going to show a little thing pop up over here that represents it. I don't like drawing these things on top of this because it tricks you into believing there's a new load that just came up. That's not what it is. All it is just the area of the load that you've already got. So I like this with the math because it stays clean and consistent with my free body diagram as I first drew it. Okay, so now we've decided that we should go to the moments, and I'm gonna sum moments. You can sum moment about any point in the system you so choose. It's always convenient to sum moments at a point where there's an unknown value. So an unknown value happens to be FYA or FYB. So either one of those points would be very convenient. And the reason why is because the moment is a force times a perpendicular distance. If I sum moments about point A, the distance to this force perpendicular from point A is 0. So it drops out of the equation. The distance to this one is 20 feet. I'll solve for that one. So what we see here, and again, I would do this, sum of the moments about A equals 0 equals the rest of this, is how I would write it. They are using a convention that we call the curl of the moment, positive counterclockwise. That is consistent with the math that actually goes behind this in theory, so that's why they use that.
When you guys do this in like college, you guys teach it as the right hand rule then?
Yes,
Or
and that is consistent with the right hand.
Right,
rule.
yeah.
Yep, that's exactly right. Yep, so if you think of this, this is X, my fingers go up to Y, my thumb is Z, but look at how my hand is curling. It's curling in that direction. The background behind this is there's actually vector analysis and cross products going on, and that agrees with a three-dimensional analysis using vector analysis and cross products. So in a 2D sense, you could go the other way and actually get the correct answer because the signs would just all switch, but mathematically it would be a little wonky. And when they get to me, they won't understand what I'm doing. So I would encourage you to consider using this. And what does this curl actually mean? So what this curl means, let's take this FYB as my force that I'm considering for the curl. And I'm considering the curl as if I pinned my beam at A. That force in the direction it is shown right now is trying to push the beam up at that end. So it's trying to take my beam and do this with it. So FYB, if I pin my beam at this point, tries to push it around like this. It's curling counterclockwise, and it agrees with a positive sense of my sign. So using that thought, let's try and figure out the moments of all of the forces on the beam. So we already said FYA has a distance of 0, so that force drops out of this equation, actually is equal to 0. We found that FXA was 0 before, so it's not going to have any impact on the moment. Furthermore, it also goes through A, so there's 0 distance. Okay, so both of those apply. Let's consider FYB. The perpendicular distance to the line of action of FYB is 20 feet. FYB times 20 feet, and it's curling, as we showed before, counterclockwise, so we put it in as a positive value. Let's look at 4,000. This was the applied concentrated load, which was at a distance of 6 feet on the original drawing.
What is this one?
Was that the 4,000 pound we're going to?
Oh,
Yep. So the 4,000 pound load, if I consider it pushing from on the beam, it's going to go clockwise, which is a negative on my sign convention. So I plug in a negative on my sign convention, and I take the 4,000 pound load times 6 feet, and that gives me the magnitude of the moment. Notice that the magnitudes of moments are coming in foot-pounds. For those of you that are familiar with things like torque in the automotive industry, that's what actually a torque is, a moment, but it happens to be a moment about an axis. So that's what a torque is, it's actually a moment.
Went through a whole mental breakdown over that in PE.
Yes. Okay, so I'm glad I made a connection, so put that in your final reason. The trickier one actually is the fact that we found this equivalent load, remember that? And we found it to be 13,000 pounds. They're gonna use that like that in this problem. You could do that times another distance, actually, that's the way I teach to the students. But sometimes when you're getting to this and learning it the first time, it's nice to have another point load that's equivalent. So that's why they did that.
How'd they
So-
know it's 10 feet?
What's that?
How'd they know it was 10 feet?
So it's centered on the beam, because the uniform load was across the whole beam. So we do the same thing, it's going to curl about A clockwise, which gives me a negative magnitude, 13,000 times 10. And this whole ball of wax equals 0. Let me stop for a second and let you think.
Where are they getting the 13,000?
That's from the previous slide.
Yep, so if you go back to this slide, they took the area of this uniform load, that times that, and that was 13,000 in units of pounds, because we crossed off feet when we did it. And they applied it at the center point, which is the center of this rectangular shape. And they're just using it again in this.
Hey, Nancy.
Chris, for that 650, why don't they just call the linear mastheads?
650.
Go back to the 650 pounds per foot.
That one?
Yeah. Is there a reason the engineers don't just call it linear mass density?
See, uniform load is acting on, it's not a mass, it's actually, it's a load acting on the system. Because if it was a mass, it would be the beam itself, it would be the unit
Nancy?
itself. And since it's something that's applied externally, it's just force on the system.
And that represents the tributary area.
Yes.
So it's not linear, it's actually,
But that 650.
The linear part of it is that it acts along the length of the beam.
right.
That's why they call it a uniform load or a linear, a linear loading, is because it's acting as units of per foot of the length of the beam.
Nancy.
Could you slide over just a little bit? Thank you.
Okay.
Yes, thank you.
All right, so now at this point, here's another thing. The more steps you skip doing in your brain, the more mistakes you're gonna make. I tell my students that I'm not smart enough to do this stuff in my head. Neither are they, even though they're way smarter than I am. You just can't, you're gonna miss something. Write down all the steps. Please. They'll skip steps. They'll go to here and they'll try to get to the answer, because they just plug it in their calculator. Have them write down the next step, which does the algebra, and the reason why is because if they try to go from here to here, they'll miss those. They'll miss the changes in signs due to the algebra. I have juniors in college that do that, and I destroy their lives for it, because that means that people die when their beams fail.
Wow.
Yeah.
Right? I mean, it's not like the toilet didn't flush. It's the beam failed, right? So this is really important stuff to me, because this stuff can easily be overlooked and it can create catastrophic effects. So they went from this step, they did some algebra, or they kind of did some combining on this, right? They did 20 FUI, they did the multiplication here, they did the multiplication here, plus 0 equals 0. They did the algebra on the next step, where they added 24,130 to each side to get a positive magnitude on the other side. They divided by 20 on each side, and they got 7,700, right? So they're basically following their algebra steps from this point forward.
I usually do this, it's helpful to me. I'll put on one side of the equation all the arrows that are going in the same direction, because they're causing the same, a moment in the same direction. And then on the other side of the equal sign, I'll put the other forces.
If that helps you understand it with the signage, that's
The
okay
signs
too.
work out.
Yeah, as long as you, if you see that this is positive on that side and that's positive on that side, and if that makes sense to you, that's fine. I mean, there's nothing wrong with it. You're basically, what you're doing is you're kind of taking these steps and combining it to this.
Yeah.
Is what you're doing.
And then they don't have to worry about whether it's,
Yeah.
Exactly.
They do have to worry about it a little bit, because if you have to be a little
knowing
careful as
which
you're doing
side
it.
to put it on.
Yes, yes. I have to say that when I teach statics, which is a class I teach every single year, which does this, I do it exactly like this. I mean, I do all the steps of the math. to the point that students are like rolling their eyes at me at the end of the class. And then they screw it up on the final and I give them 50s. Because they don't do this. So I keep on I'm hammering this until it has no sound, but it's amazing how many times this mistake happens. Okay, so what this shows us is that the moment calculation gives us one of the reactions outright.
And it's really easy to plug that back in, so.
And then,
that's-
yep, so now you go back to the equation you found back here that you couldn't solve. And now you can because you plug in the one you know, you do some algebra, and you get the other one. And notice they're not equal. So this gives me a reaction of 0 of FXA, 9300 of FYA, and 7700 of FYB. Give me a good observation of why you think a number is right on there. Go ahead.
Well, your 4,000-pound load is closer to A than it is to B, so you expect it to be.
Yeah, you-
Exactly right. I called them reality checks. Let's look at this and see if we got a reality check on this. And because this 4,000-pound load is kind of leaning to the left side, that one ought to be bigger than that one with that loading. Right? And I mean, you can't say the numbers just off the top of your head without doing the calculations, but you can see the effect.
And you could certainly prove the students, just have them hold like a 2x4 between
Uh-huh.
two students and move the weight between it and
Yeah.
ask them, are you feeling more weight, less weight?
Yep.
It was interesting, I was trying to just quickly look at it as a proportion issue, like.
It works that way.
It does?
It does, yes. So when I said before that you could do this by the fancy word for add superposition, you could do this uniform load of 650 times 20 divided by 2, gives equal loads there. Plus 4,000 times 14 divided by 20 there. And that one has 4,000 times 6 divided by 20 there added to it, and you get the same result. So you can use linear proportions to do that. But you're starting to get into tricky business
Yeah, 'cause
with the students, because now what you're doing is you're introducing little shortcuts and things that
Don't always apply.
that don't always apply, one, and you might blow their minds too, and on the first go around. I'd rather do the math a couple times and then say, hey, can we do this easier? And then maybe show those proportions, same, got the same. Sort of. There's not two unknowns in this one, so it's not really a system of linear equations. It is and it isn't. I mean, when I think of a system of linear equations, I got FA and FIB equals 70,000, FYA and FIB equals some other value and solve the two or whatever, you know? So that's what I think of, then I would actually have to go through, you know, a substitution or whatever to get that thing to happen. But I get the point they're trying to
Use it in.
Okay.
Yeah, right, okay. Yeah, moving on. Let's talk about, now that we found the reactions, how do we draw what's called the shear and moment diagrams? This is what we use to design that beam. So the magnitudes that we get from this and from the moment diagram on the next slide give us those properties that I've been talking about so that we can figure out whether the piece of steel is good enough. All right, so we've solved reactions. Here's how this works. There's a ton of background noise that we're going to glance over and omit. But here's the rules to draw these for the cases that you will see. Whenever you have a concentrated load on the original loading diagram, it will spike this diagram up or down at that point. Whenever you have a uniform load, and you have to use the uniform load, why I don't like this, why I don't like this thing. Okay, that's not the original loading, that's an equivalent loading. We have to use the original loading diagram with the reactions we found. Whenever we've got a uniform load, it changes linearly, up or down. If it's pushing down, it pushes down. If this happens to be pushing up at one point, it pushes up. Okay, so watch how this goes. We have FYA of 9,300 pounds. We start at 0. We spike up 9,300 pounds because at any concentration, spikes up, reactions count. from that point forward, the uniform load is going to push the shear down up to that point where something changes. And it's going to push the shear down the area of the loading up to that point. 650 times 6. So we take 9,300 minus 60, times 6 gets me to that point. Trying to figure out in my head, I think that 650 times 6 is just the 3,900, and that's just the height that is changing. So 9,300 minus 3,900 equals the value at that point. Okay, yep, the 650 pounds per foot is the slope of that line. So here's your real math connection. This magnitude that they show here is the slope of the next diagram. If you really want to blow their minds, you could say, hey, that's calculus. That's actually what that is. It's an interval. So 9,300 minus 3,900 gets me to that. I don't have the math for that because they didn't give me that. They might give me that point if I keep clicking. Spikes down 4,000. Now it gets to 1,400. Then my uniform load starts again, and it goes all the way to the end of the beam. The uniform load keeps sloping down. Don't worry that it crosses 0, just let it keep going. All the way down to the point, and it should at the end equal 7,700. So if I took 1,400 minus 650 times 14, I should get negative 7,700. When I get to negative 7,700, I'm not done yet because I got one more concentrated load, which spikes me back to 0. It should end at 0.
For the homework, do we need to do this?
Yes. Yep. Yep, so let me see if I can, does anybody have a calculator out that I can write some numbers? So take 9,300 minus 3,900, what does that give me for the magnitude?
5,400.
5,400?
Yeah.
Yep, that's a spot that they should have, and maybe if I click it'll come. Then it drops 4,000, it gets me down to 1,400, so this spot is 1,400. And then I subtract off 650, which is the height of this, times 1,400, which is the length, that gives me negative 7,700.
I'm sorry, how do you get that last number again?
Start at 1,400, subtract the area of this, which is 650 times 14.
Okay.
And that gives me that value, and then I spike back up the reaction.
So if you don't have a uniform load, does it just become a piecewise function then?
Yeah, it just keeps going. So if I only had this, if I had this, foreshadowing. My shear diagram for this qualitatively should look like this. Assuming the beam has no weight, weightless steel is awesome. It's great to use in buildings. Spike up, uniform because nothing's happening in between that point and that point, so it just stays constant. Spike down, nothing's happening. Spike down, nothing's happening. Spike back up as the reaction at the end.
Oh, I made this.
So if nothing's happening, there's no loading in between points, just keep going straight on your shear diagram because the shear is the measure of the shear as a function of the length of the beam from 0 to L. Here's the tricky part, the moment diagram. Trickier, not really tricky. Does this make sense so far? So I mean, if I threw another load on there, it would add another spike maybe or whatever.
So, I understand the diagram, how you got it.
Yep.
How are we gonna use it? Is that it?
Yeah, well, no, that's a great question, because for two things. 9,300 pounds is the maximum shear. We need to compare that to the shear capacity of the beam when we analyze the beam, because it's got a shear capacity to it. And this 9,300 pounds was its reaction. That's how many bolts and welds and plate we need to handle to support it. Which we don't get to in the curriculum, but that's the next step.
So that negative 7,700 is what?
Actually, a positive, it's the same thing on the other side. right? Yeah, so, yeah, we would use the absolute value, right? Because it's a, both of these are actually spikes up. This just happens to be across the length. So at this point, I've ended it here at the beam, and then I spike up to 0. That's the reaction that needs to hold, so that's how many bolts and welds I would need to handle on that side.
So why is it on that diagram, your spikes are vertical, but this one's slope?
I'm spiked vertical here. You mean between?
Yes.
Because this uniform load, when I've got a uniform load acting on it, it's pushing it down uniformly. between the members. In that one, over there, I've got nothing in between there, so it just stays constant.
Because there wasn't a W given, there wasn't a uniform load given in that one.
Correct.
It's just the 2 point loads.
Correct, and point loads only make spikes up and down like this. Uniform loads make slopes between the points.
You get that weightless steel at the same place you buy friction surface.
Yeah, they got it at Menards.
And a board.
Yeah, we're at Menards.
Sell a board set for this too.
So over here on our, one over here, we break that into 3 sections
Yep.
of whatever, 25 divided by 3 would be.
Yes, yep, and then, and you down up with the shear diagram would look a little like that. It would look a lot like that with numbers. This line? That's just like an axis that you're using to, so the shear is a measure of the magnitude of shear as a function of the length of the beam. So they're just showing something to draw off of, so it gives you a 0 line.
8 feet, there's no shot.
So how's that located from scratch?
Yeah, if I was starting this, so if I was starting this from scratch, and I were to draw, that would be the starting point. And then I would start drawing from there. Right, so this horizontal line here is just simply a 0 line to work with as if you're drawing an X and Y axis. It starts at 0. The magnitude is 0. So when I take this and I measure the shear right at the end of this beam, the first thing it does is spike up from 0 to 9,300 due to that reaction.
So, I don't know if this is a connection or not, but at 0, where the shear diagram is giving, so like 6 foot plus X.
Right
keep going.
there.
Yep, is that where if the beam were to split, that would
That's a great observation.
What'd you say?
So the question was, Beth's wondering, what happens at this point where it crosses 0? What a great observation.
I thought that's where it would break.
It's, yeah, well, not,
Or
break is-
shear.
break is a strong term.
Shear.
Binge.
Hold that thought for a second.
Is that the point where the maximum deflection happens?
Yes, and something else. Let's go to the next step.
Okay.
This is the shear diagram. So they've got a little discussion of this, which we actually just talked about. Let's draw a moment diagram. So I've got the shear diagram, let's use it to draw the moment diagram. The first thing that I need to do is locate where it crosses 0. So the location of this distance x is the location from this point where it crosses 0. This is actually a linear equation that they don't show the whole thing, so I'll write it out for you. It's the equation of a line, y equals mx plus b. M is 650, that's a slope, we said that, right? B is 1400 based off of this. So if I take 1400 minus 650, x equals 0, notice that what they did was they moved this to the other side, divided by 650, and solve for x. Okay, so it's just simply the equation of a line. So when I look at this, what I'm looking at is where is the last stop point that I know of, and I look at that triangle such that I know that that magnitude is 0, and I can use the slope to figure out what that distance is.
Would it also work if they do enough trig to just use the triangle for that?
They could use a triangle for it too, yep. Yep. Or they could locate it from this side too, they've got a triangle that they could work with from that side, that they know the height of this, they could figure out the length of this. I mean, there's lots of ways you can handle that.
Chris?
Yep.
Can you say that one more time with the equation of a line?
Yep, so the equation of the line, so it's y equals mx plus b. So this is mx and b.
Right.
So we know that the Y we're looking for is 0. So we already know that value that we got. We start at the point that was last observable on the little triangle, which is 1400. And then because the line is sloping down, it's negative. The slope of the line is the 650 pounds per foot from the original line. So it's 1400 minus 650 times the distance equals 0.
Okay, thank you.
So you're,
Now, Beth's question. The location where the shear crosses 0 creates a maxima or a minima on the moment diagram. Because it's calculus again. So, here's how we figure this out. This point, which is the most interesting point on it, is the maximum moment that the beam is going to need to resist. So I'm bending this beam with whatever I got bending it. It's got a maximum moment to it. It has to resist at least that much, and we'll show you how to do that in the afternoon when we talk about beam design. This point is equal to the area of this underneath the shear diagram. And I think they're actually gonna highlight it in a second.
kink.
So, well, yeah, so yeah, it does kink because this happens. So you changed your magnitude abruptly there. But the magnitude of this point is equal to this area. And that's how they do it in the curriculum, is they look at that. So what they do is they take the area of, they kind of break it in piecewise into a triangle, a rectangle, and another triangle. That's fine. That point is also the area of that triangle, which nobody observes because you just start reading left to right.
What, repeat that, I missed that, I was
Yep.
writing, repeat that.
Yep.
Oh, that triangle, okay.
So that point also equals that area. Okay? So, but that takes a little bit of thinking, because your brain kind of starts here and thinks here, and then they do the math off of this, and they do the areas of under the shear, and the area of this little shape that's triangle plus rectangle plus triangle equals the magnitude of that. 7,700 times whatever this distance is divided by 2 also equals that. So what I encourage you to do is let your students think about which one's easier.
That one.
Because the one on the right is actually easier to do. Yeah. So let's see that happens, okay? So let me erase this. Go to the next slide. So here's what they do in a mathematical sense first, which is valid 2. They cut this thing right at the point where it crosses 0. And they sum moments about this point backwards to get all of these forces. So this map that they're showing here is valid if you were to run it, and it would give you the magnitude of the internal moment of the beam, which is what we're measuring at the moment. This is a mathematically true way of doing this. There's a better way to do it, which is just use the areas. So, are they gonna give me an answer here? Yeah, so keep this number in your pocket for a second. Let's kind of gloss this for a bit, and we can come back to it if you want to. But we're gonna see that this 45,608, with a little rounding perhaps, is gonna be the same thing as the areas.
Did they pick the left side of the beam because you have the 9,300 pound, which is your maximum shear force?
I think they just picked half of the beam. I don't know that they thought any harder than that.
Okay.
Because I could have picked the right side of the beam, which had a uniform load, and the 7,700, and gotten the same 45,600.
Okay.
Let's do it this way. What did they do over here? So they got the maximum. Okay. This is what I was showing before, which is that they did it based off of the area under the shear diagram, and colors are useful in this. So color the areas. And what they do is they say, all right, find the area of triangle A and rectangle B and triangle C, and that will equal the 45,608.
And that should, in theory, equal the area of the right triangle?
Yep, it will. I mean, with a little rounding perhaps, because This 2.15 is probably from the answer. So we would be with a foot pounder. So all right, for you math wonks, we're integrating across a distance from 0 to this distance. That's all we're doing.
Yeah, same.
Right? We're finding the area under a curve. Piecewise with shapes we like. So area of A, it's 3,900 tall, which is why they gave us that in the first place when we were doing our reactions, times 6 divided by 2. That's the first piece. Area B is 6 feet times 5,400, 4,000 plus 1,400. And area C is 1/2 times 2.15 times 1,400. And that gives me 45,605, which is a little bit different than 45,608, which they got based off of the math. There's a little rounding involved. Is that what you got?
Well, on the other side, I got 45,622.
That's what I got.
Yeah, so again, I wonder if you let this stretch out the full thing. And I also wonder if this was rounded at some point too. So I mean, you got a few values that they've been gathering some error, if you will, but I mean, we're within what, 0.5% or something like that? So we're pretty close between the two sides. So if you carry all these out 20 decimal points, you should get a value that's exactly the same.
For purposes of the submission,
Uh-huh.
as long as we are, within
Yep.
reason.
Yeah, within reason. Yours is gonna be a lot easier because you're gonna have a rectangle, so it'll be easy to calculate. Yep. Yeah, whenever I look at students' work, the first thing I look at is, did you do the process right? If you mashed a number in your calculator wrong, that's a thing, but it's, that's an easy correction. Do you understand what you're doing? That's the bigger thing.
Which is why they don't get the credit that they should.
Well, exactly right. I mean, we don't wanna just be consumers of knowledge. We wanna actually know what we're doing. So Google can probably do this for us, but that doesn't mean we understand. I don't know if they do the triangle on the other side.
They don't.
They don't, okay.
Just curious.
Okay. Let's say for practical purposes, I've shoved them off in your brain for the time being, and we're gonna make this a little bit of work time and get yourself around yourself. Lunch happens in 20 minutes, we can go to lunch then. When we come back, we're gonna open up MD Solids and we're gonna start to do some MD Solids work. That's what this figures comes from. And this is an example of how we do a uniform load. And we'll do this one in MD Solids so I can show you how to use the program. And then you can go back after the fact if you choose and do it by hand and prove that you know how to do it. And so they've got the solution in here using MD Solids. We'll launch this one as our introduction of how to use MD Solids after break. And then once we've got that, we'll go to beam design, use maybe what we learned, and figure out how to select the beam appropriately. So there's a fair amount of meat yet this afternoon to think about. Are we doing okay? I haven't created too much stress? Paul's over there is like, I think there's some stress. There might be a little stress. So that's all right. Stress is good. We can overcome it.
Chris?
Yes.
So when we're doing one for the magical massless beam.
Yep.
Would the max moment be basically in between the two piecewise? So when you draw it out, it'd be
Qualitatively, slope, straight, slope.
Exactly. Gotcha.
Yep.
Thank you.
So this creates, and we'll talk about the relationship between those things after lunch too, when we start using MD Solids to show a few figures.
Awesome.
Awesome.
Hey, Chris.
Yep.